So good afternoon. We have seen in the previous lectures that ranking is extremely important. So we have seen at the beginning results that are relevant in the Boolean retrieval model, in which basically there is no ranking. Then we introduced the concept of ranking, and we observed that ranking is extremely useful in order to deliver the proper content to the users, but at the same time must be done effectively and efficiently, because basically users are going to look at only the first and the top pages in ranking. Okay, so it's an extremely useful tool, in particular for non-expert users, to avoid to explore a wide range of possible results, but must be done extremely efficiently in order to avoid, for this reason, right? Because users are only looking at the top pages in the rank. Okay, so now the main problem we want to address today is how to evaluate the performance of an information retrieval system, and we will start with a ranked evaluation, moving towards ranked one. Okay, what are possible metrics to evaluate the performance of a search engine? One possible metric that is of interest, clearly, of the service provider is how fast the index is built. One possibility is to use the number of bytes per hour. Another possible metric, which is actually related to the user, is how fast is the search feature. Okay? So how many queries I can handle per second. Or what is the cost per query? Clearly there is a significant infrastructure cost. So the question here is to understand what is the cost per query. Those are all possible metrics. What is nice in those metrics is that are very clearly measurable. So you have very precise metrics, which are speed, size, or money, in order to understand what are the performance of the system according to the other metrics. But actually, they do not capture the main objective of a search engine, which is to provide a query that is significant for the user. In other terms, if you want a wider definition, we want to make the user happy. So how can we capture this user happiness? And what is the user happiness? There are a number of factors. It can be the speed of response. It can be the size of the index, as we saw before. So this is the reason behind the ranking. It can be a well-done user interface, but clearly, since we are in the context of search engine, the most important part is the relevance of the result set with respect to the user need. Okay? I remind you that the idea here is the user has a need, translate it into a query. This query is provided to the search engine that provides you back a set of relevant answers to those queries. So we want to measure this, this relevance. That's interesting, in particular nowadays, in which most of those services are, for the end user at least, free. It could be that being free is a relevant option. But again, why do you choose Google rather than other web searching engine? Okay, most likely is because both of them are free, both of those options are free, but because maybe Google will provide you better results in terms of relevance. Okay, clearly, you cannot consider only one metric, because assume that you have very relevant documents for your query, but those are provided in 1 year. Okay, there are studies in which basically you expect to get results after few seconds at most. Okay, actually fraction of seconds. Okay? So you have to combine relevance with being free, with being fast, and so on and so forth. Okay, anyway, the question here is to what extent and what are the techniques in order to evaluate the user happiness in terms of relevance. So what is actually that makes a user happy? Clearly, it depends on what we consider as users, right? If we consider the searcher, actually, the main goal in order to make it happy, or her or he happy, is to find what she was looking for. So measure the rate of return to this search engine. If you consider the advertiser, clearly, is how many clicks you have on your advertising banner. If you consider a buyer, is to what extent you, at the end, after your search, you buy something. If you consider the seller, how much do you sell, and so on and so forth, right? And you have also something that maybe you do not consider, but web search engine are also used for increase the productiveness. Okay, I mean, as a student, most likely you know it, because whenever you have a topic that maybe you don't understand or you want to go into more details, you search on the Google engine, on the search engine in order to get some results. Yep. So it depends on who are the user. Anyway, in terms of user happiness, again, the main metrics we want to consider is the relevance of the result set with respect to the user needs. And in general, again, remember that user need and query are different concepts. And the query is the tool through which the user specify his or her needs. And one important topic is to what extent this is simple, this is possible, the user is expert enough in order to make this translation. Okay, how do we measure relevance? Basically, we need 3 elements. We need a benchmark document collection, so something through which we can run some experiments. A benchmark suite of queries over this collection. So those are documents, those are queries over these documents. And then clearly an assessment, a metric, to evaluate the relevance for each query document pair. Okay, this is the idea. Okay, again, relevance to what? Even if, in principle, the relevance should be about the user needs, the information needs, actually, we are considering the relevance to the query. Again, here you see, let's consider this, even if this is problematic. Here, considering this information need, I'm looking for information on whether drinking red wine is more effective at reducing your risk of heart attacks than white wine. Okay, so this is your user need. This is the information need. You can translate it into this query: red wine, white wine, heart attack. Okay, this is most likely something that you will do. But what is problematic here is that this document, D prime, at the heart of his speech was an attack on the wine industry lobby for downplaying the role of red and white wine in drunk driving. which is actually not related to our information need, but is very consistent with the query. Okay? So those are the kind of issues that we have to consider. Namely, D prime is a very good match for the query, but at the same time is not related at all, or only marginally, with the information need. Anyway, still, we will consider the relevant to the query. Okay? Even if we should consider information need, we will consider the query because it's the most, it's easier actually, okay? But please keep in mind that there are the problems, the issues we discussed before. Okay, what can we do? We already saw those concepts. We can do the following. We can measure precision and recall, okay, of the system. What is the precision? Is the fraction of retrieved documents that are relevant to the query. So basically the precision is over all the retrieved items, what are the relevant items that are retrieved. And the recall is the fraction of the relevant documents that are retrieved. Okay? Okay, notice that the denominator here is different. Okay, this is important. Here we are the retrieved items, namely the answer to our query. Here are the relevant items that not necessarily are provided by the system to our query. Okay, so basically we can transform these in, we can see this picture in which you can have either retrieved or not retrieved document. You can have either relevant or non-relevant document. So we call it a true positive retrieved and relevant document. We call it false negative document that are relevant but are not retrieved. And then we call false positive document that are retrieved but are not relevant. So basically I'll give you those documents but are not relevant for the query. And true negative document that are neither retrieved nor relevant. Okay? So remind that here we have a binary system. A document is either relative, is either relevant or not relevant. Okay? In this particular case. Okay, in this picture you can see the difference in the denominator. While in the precision I consider all the retrieved document, and I'm only interested in evaluating the fraction of all the retrieved document that are relevant. In the recall, I consider all the relevant documents, and I'm interested in evaluating how much of those relevant documents are provided back by our system. Is this clear to everybody? Okay. Good. Think about it. Can you tell me whether there is some kind of relationship between the precision and the recall? So let's make the simplest question. How can I increase the recall? Again, let's see what is recall. Recall is the fraction of relevant documents over the retrieved ones. How can I increase the recall? If I return all the documents, clearly I increase the recall. Does it make sense? Okay. And what happens to the precision in that case? Usually it will decrease, right? Because basically I am putting into the picture a lot of documents that are not relevant. And also keep in mind that usually the number of non-relevant documents is much bigger than the number of relevant ones, right? Okay. Good. And so please remember this observation because allow us to grasp why using accuracy, which is another possible metric, is not a good idea. But we will see it later on. Okay? So clearly, as we observed, you can increase the recall by returning more documents, possibly all the documents. Indeed, the recall is a non-decreasing function of the number of documents, and this is pretty clear from the definition. And actually, if you answer with all the documents in a collection, you get a 100% recall. Okay? And usually it's also through the converse. It's easier to get high precision for very low recall. Okay, assume that the document with the largest score is relevant. How can we maximize precision? Okay, we can maximize precision simply providing back only that document, right? Only the document, the precision is 100%, is 1. Because basically the only document that I provide you back is relevant. That's it. Okay, since now we have understood that there is a trade-off between precision and recall, the question is, how can I evaluate, I can measure, I can trade off between those two metrics? And this is the concept of a combined measure named F. Okay, let's see the definition. Now focus here. Here you have this alpha parameter, okay? You can put alpha either to 0, you can give to alpha any value between 0 and 1. And basically it allows you to weight whether you are more interested in precision or whether you are more interested in recall. If you put alpha equal to 0, this term disappears, and thus basically you are not considering precision. If you put alpha equal to 1, this term disappears, and thus you do not consider recall. Okay, so basically you have a tuning parameter alpha. In many cases, actually, instead of alpha, you consider beta, but it's basically the same. And clearly, in a number of cases, I would say the most frequently used F, assume that you have beta equal to 1 or if alpha equal to 0.5. Namely, you equally balance precision and recall. Okay, and so basically what you get is an harmonic mean of precision and recall. Okay, so let's make a very simple example. Okay, so this is the matrix, the array matrix we saw before. And let's compute the precision and the recall. So all the relevant documents are 20 plus 40, so are 60. And so the precision is 20, the ones that I actually retrieve over all the relevant, okay? And the recall is 20 plus 60, which is basically the relevant ones, over the ones that I actually retrieve, okay? We simply applied the definition. Good. So basically, what we can do now, we can compute, assuming that beta, as in this case, is equal to 1 or alpha is equal to 0.5, we can compute F simply as twice 1 over P and 1 over R. Okay, and this is a measure, a combined measure of precision and recall. Okay? Okay, again, precision. How many among the retrieved documents are relevant for my query? Recall, how many relevant documents among the total relevant documents I provided back. Okay? Good. So why accuracy is not a good idea? Apparently, you know, what is accuracy? First of all, accuracy is the fraction of decision, either relevant or not relevant, that are correct. Okay, either relevant or not relevant documents that are correct. Why is not a good idea? Remember the observation we made before. A significant fraction of the documents are usually not relevant for a given query. Okay? So this true n is usually very high. Is very high, right? It's very big, yes. True negative, which means documents that are not actually relevant for our query. This number is usually very high. So basically, this fraction, you know, it's very biased by the fact that this number is very high. So according to this observation, can you please tell me what is a system that will provide always a very good accuracy? Do you have in mind any idea? Right. That never return anything. Because here is 0, here is 0. This is pretty big, is a significant fraction of the total. So a significant fraction of the total over the total documents is very high. So accuracy will always be very high. This does make sense to everybody. Okay, again, a system that will not provide back any answer to any documents for our query means that TP is equal to 0. Tn is always a significant fraction, we observed, of the overall set of documents. And so Tn over this is roughly 1. Okay? Okay, so this is indeed the example of the Snoogle.com. It's a search engine that will always return 0 results, as you observed. Okay? And clearly, this will have always a very high accuracy. Let's see an example. So, the returned documents are 0 in our Snoogle search engine. Now, usually the true negative are big. The other fraction is the false negative is usually relatively small. And thus we have something that is, in this particular case, 270 over 300. So a very high accuracy, even if I didn't provide back any document. So accuracy is not good. That's why it's better to consider alternative metrics among the ones precision and recall and depth are good option, are the standard option. Questions?
So accuracy, which kind of information?
Accuracy actually tell you.
I mean, if the system is
accuracy can be, a good metric, but you see, you have those extreme cases in which it's meaningless. which does not mean that it's meaningless in all the cases.
If either system is good or bad, accuracy could be the same value.
No, accuracy is not the same, but you see, this is from the happiness point of view, from the relevance point of view, is extremely bad, and at the same time, accuracy is very high. So this is the problem. It doesn't capture problems in the system. Other questions? Okay, indeed, a simple trick to maximize accuracy is, as we observed before, according to the observation we made, is always say no. Always say there are no documents matching your query, and you get a very high accuracy. Unfortunately, as we observed, this is very bad, because in our search engine, it's preferable to provide wrong results, but also relevant ones, rather than do not provide anything. I mean, a search engine is designed for this purpose. Okay? So accuracy does not work. And that's why we use precision, recall, and depth for the evaluation of our system. Okay? So now, again, why the harmonic mean? Why we don't use a arithmetic mean as an example for precision and recall? Okay? Remember that according to our definition, to the definition actually, now let's take the simplest one. We are averaging with harmonic mean, 1 over f, 1 over r. We are not averaging with arithmetic mean as an example. Why? Okay, because the arithmetic mean is basically you get 50%, which is 50% of returning everything. So it does not have the power of discriminate among the different cases, which is basically too high. The 50% of return everything does not discriminate between system in which you want more precision and system in which you want more recall. What you would like is actually to punish really bad performance, either on precision or on recall. Systems that are very bad in precision or recall, or either in precision or in recall, must be punished. Okay? Can you give me an example? Okay, maybe I didn't make a main observation. Do you believe exists a system or, say, a solution that always is the best, in the sense that I have always to, I don't know, prefer precision rather than recall, or vice versa? You are a designer of a system, okay? A client comes to you asking for the design and implementation of a search engine, okay? Do you believe there is a solution that must be always implemented, or there are different cases? Okay, let's make a very typical example. If you have to implement a search engine for lawyers, okay, would you prefer precision or recall? Actually, usually lawyers prefer recall. Why? Because they are more interested in obtaining all the relevant results, and then they dig into the relevant results in order to see whether they are interested or not, rather than have only a limited fraction of those relevant results, but very precise. Okay? This is the classical example. Usually, lawyers or classes of users like lawyers or low search engine are preferable to have a very good recall, which does not mean clearly that you you don't need precision. But if you have to move the parameter in order to tune whether you prefer recall or precision, usually you move towards recall, which is not the case for other users. Okay, maybe that usually users need or are interested in more precise in the sense that with web search engine with precision, which is higher than for the lawyers. Okay, this is the more or less the idea. So depending on your user needs, you have to understand what is the correct trade-off between precision and recall. There is not a single solution. But then we have to understand how to compare different systems, and this is the purpose of the next slides. But now let's go forward. The idea is that we want to punish, anyway, really bad performance, both in precision and recall, okay? And so we could take the minimum, but the minimum, it will be clear, is not a smooth function. And well, the harmonic mean is a kind of smooth function that, to some extent, approximate this minimum. Let's see it in this picture. Okay. So this is the maximum. This is the minimum of a given system. And you see the harmonic. Okay, the harmonic is some kind of a smooth approximation of the minimum. Another good explanation on why to compare precision and recall we need the harmonic mean is with this example that you find in Stack Overflow. And it is very nice to me. I mean, I think it's very significant. Assume that you want to compute what is the average of a system running on 30 and 40 miles per hour. Okay. If you drive 1 hour for each of the two speeds, you will get the average that is 35. 1 hour at 30 miles per hour, 1 hour at 40 miles per hour. Okay. You combine 30 plus 40 divided by 2, 70. Now, if instead of the same time, you are considering the same distance, you need a different number, right? Because it's not anymore, I mean, either you compare time with time or distance with distance, but you cannot compare distance with time. Now, if you recall precision and recall, the denominator is different, while the denominator is the same. So what you do is you consider the reciprocal, because simply you are considering hour with hour or distance with distance. And this is why the harmonic mean makes sense. Okay? Okay, good. The fact is that we remember the three ingredients. Now we have a metric, or actually we have, yes, okay, a metric F or metric P or metric R, precision, recall, or F in order to evaluate our system. But anyway, we need relevance judgment. So we need a collection of documents, we need a query, and we need somebody telling us, okay, according to this query, this document is relevant, this document is relevant, this document is not relevant, not relevant, relevant, okay? The problem with this is that having this kind of data set is very expensive. It requires time, it requires effort, it requires money, okay? It's very difficult, but we will see it. There are some collections available, but keep in mind this is a difficult task. Okay? Up to now, we didn't consider the rank at all, right? Why? We consider only retrieved documents, set of retrieved documents, and then we say relevant or not relevant. But we didn't say in the set of the retrieved documents, this is document number 1, this is document with rank 1, document with rank 2, and so on and so forth, right? So we didn't consider this. While we argumented on the fact that modern web search engine actually needs a ranking. So the question is, okay, now I can evaluate a system that is not ranking. What can I do with a ranked system? And so the purpose of the next slides is to evaluate, is to discuss the ranked evaluation. But before going further, are there questions? So concept. We need 3 ingredients: collection, metric, collection, queries, and for each query document pair, an evaluation, a judgment. Okay. Once we have these, we have 2 main metrics: precision and recall. Okay. And then we discuss the trade-off between precision and recall, and we say in order to have a combined metric to evaluate precision and recall, we consider F, which is an harmonic mean of precision and recall. And we can tune the alpha or beta parameter in order to define whether we are more interested in our evaluation on precision or whether we are interested in our evaluation in recall. Okay? Good. Now, as we already observed, precision, recall, and effort are measured for unranked sets. So we don't have, while actually we want to measure ranked lists, because basically the result set of our search engine is actually a ranked list of the retrieved document. Okay, so what can we do? The most, straightforward solution is to compute all these metrics, precision and recall, for the first entry, for the first, document in the list, for the first 2 documents in the list, for the first 3 documents in the list, and so on. Okay, so measure the metrics precision and recall for each prefix. Okay, and with these, we can basically build what is called the precision recall curve. With respect to the slides I'm using now, now moving to another set of slides, and then I will provide you the references. But anyway, it's the link that you see on top of the slide. Okay, so in this case, what we want to do is we want basically to define a threshold. This threshold clearly can move. Okay, the dark green documents are the relevant one. The light gray documents are the not relevant ones with respect to our query. And what we want to do is we want to compute precision and recall of the first n documents of the retrieved list. Okay, this is the idea. So the first one, the first 2, the first 3, the first 4, and so on and so forth. So anytime we have to consider a threshold, and clearly we want to compute 2 systems now, because the purpose of this evaluation is to see whether system A with a particular ranking algorithm will perform better or worse than system B with another algorithm. Okay? Okay, let's see an example. So those are the relevant documents, and assume that you get those two rankings with two distinct search engine, okay, information retrieval system. Okay, what is the precision here? The precision is 1 over 1. I'll provide, if I'm here, I provide you one document, that document is relevant, precision is 1. This document is 1 among the 6, and so the recall, okay? So now, first two, the precision drops to 0.5. Why? Because among the two, one is relevant, the other is not relevant. So I'll give you two documents, one is relevant, the other is not relevant, so precision is 0.5. Recall didn't change. Why? Because the document relevant is as before, nothing changed. Okay? And so on and so forth. Okay? This is the kind of evaluation I have to do. Is this clear to everybody? So, I'm moving the threshold and I calculate precision and recall for two different systems that provide two different rankings, clearly. Okay? And now I want to compare those two systems. Okay? So now, as an example here, the precision is 0. Why? Because among the only document that I provide as answer to the query, it is not relevant. Similarly, the recall. Now here, among the two documents, only one is relevant, and so on, and this 0, this is as in the case before, okay? Among the two, only one. Sorry, the 6, only one, okay? Good. So now I can basically plot a curve in which I have recall, I have precision for all the documents. Okay? Simply, I keep those values and I plot precision and recall for both the two systems. And thus, I will get this point, you see, as an example here. As an example here, the precision drops to 0.5. Why? Because among the two documents, only one is relevant, while the recall remains the same. So I can plot this point. And I have two distinct curves, one for the system A, ranking A, and one for the system B, ranking B. Okay, now the question is, how can I compare those two systems? How can I say whether one is better than the other? Okay, one point is the following. Clearly, we have those points according to the query we made and the ranking list provided back by the system. But as an example, let's observe here. What is, for those two systems, the precision at 0.5? There are no points here, right? So we need some kind of interpolation which allows us to build a continuous curve that allows us to compare the two systems. Okay, we need to interpolate. How? Is this clear? The problem here is the following. When we are at 0.5, basically there is no point. Remind that in this graph, even if we have those lines connected the points, those are artificial, actually. The points are the real, have a meaning, but the lines are simply to connect the points. Okay. So, what can we do? We can interpolate, as we say. What kind of interpolation can we use? The idea is that we remember that on average, the recall increases and the precision decreases. So we want an interpolation curve that well represents this general behavior. And in order to well represent this general behavior, basically what we do, for each point, we consider the maximum value on the right, okay? And so we get this interpolation for this point, this and this. So basically what we are saying, even if we don't know, actually, according to our curves, what would be a value of the precision when the recall is between 0 and 0.2, through this interpolation, I have that the precision will always be 1. Okay, and this interpolation allows us to guarantee that on average, precision drops as recall increases. Let's see, precision drops as recall increases. So I have this kind of curves. Okay. Clearly, then what can I do? I can simply take the average between the two in order to build a curve that basically distinguish the two systems. Okay? So the problem is that I have points. I do not have curves. So what I want to do, I want a general purpose mechanism to compare two systems. So what can I do is I can interpolate the points in order to generate two curves. Okay? This interpolation, according to the observation that on average precision drops as the recall increases, can be done looking at the maximum point on the right, which brings us to those two curves. And then clearly I can make the average in order to have a kind of separation line between the two systems. Okay, so now we have finally a system in order to compare, a mechanism, sorry, in order to compare two systems, right? Because now we can have such kind of curve. I have recall precision. I build the different curves for system A, system B, system C. And now what can I do? Okay, let's observe this picture. Let's consider system A as the reference one, the ones that we want to evaluate. Question, is system A better or worse than system C? Well, system A, according to this curve, has always both precision and recall better than system C, so definitely is better. There are no reason to select C instead of A, because both precision and recall are always better. Now, what happens to system B? Well, this is a different story, right? If I'm here, so if I take a recall equal to 0.roughly 5, I don't know, well, actually system B is better than system A. But if I'm there, on the other side, it's the vice versa. So it's up to you to decide whether you want to use system A or system B, depending on where you want to have a better recall or a better precision. Okay? This is the kind of argument through which you can compare two systems. Questions? Everything clear? Okay. Good. So now we have a mechanism through which we can evaluate two systems. But okay, usually, you know, instead of having a curve, which is fantastic, but to some extent is not synthetic, if you have to compare a number of systems, you probably would need a single value. Okay? And this is the purpose of this mean average precision, which is actually used in many research papers. Okay? What you can do is you can take the mean of the average precision across a number of queries. Let's see. The example, maybe it's easier. Okay, now, this is the precision of query number 1, and is actually I think is missing something. Anyway, is the precision that you see here. And the average is simply the average divided by the number of documents. Okay? So this is the average precision of query number 2 for the two systems. Okay? We have two systems that we want to compare. And we have two queries now. Two systems and two queries, while before we have two systems, one single query with two different rankings because of the two systems. Okay, now we get this average precision for query number 1 and query number 2. What we want a synthetic number to evaluate to how much is how good is the system. What we do, we sum up for the two distinct queries, and then we divide it by 2. And clearly you can iterate this argument with as many queries as you want. And so you get a synthetic number over a set of queries defining you what is the mean average precision of your system. Okay? Good. Now, up to now, we consider binary evaluation, either relevant or not relevant. But we can consider other evaluation in which you might ask to the judges. I remind you, we have a collection, we have query. For each query document, we have a judgment. Up to now, the judgment, what is relevant or not relevant, but you might ask to the judges to say, to give you a number that defines to what extent the document is relevant. Okay, so it's not anymore 1 or 0, it can be any number between 1 and 0, which gives you the marginal relevance of a given document. Okay? In general, the lower the ranked position of a document, of a relevant document, the less useful is the document for the user. But again, don't forget now that instead of having 0 and 1, relevant or not relevant, we have a value telling you what is the evaluation of the relevance of a document for the ones, namely the judges that are providing you the ground truth. Okay, if you have this value, which is between 0 and R, or 0 and 1, but not only 0 and 1, any number between 1 or 0 and R, what you can do, you can have a cumulative gain, okay? Assuming that the ratings of the documents are R1, R2, R3, the cumulative gain is the sum over the ranking of the documents. Okay? As usual, if you take a linear I mean, if you sum up the value, the marginal contribution of all the document can be too high. Since we have the assumption that the relevance of the documents is proportional to the ranking, as bigger is the ranking, as much the documents is relevant, we apply this logarithmic factor in order to smooth the contribution of each document. Okay? Good, so let's see an example. Assume that you have T-ranked document with the relevance which is between 0 and 3. Okay, so the first document is ranked 3, the second document is ranked 2, the third document is ranked 3, and so on and so forth. Okay? Clearly, what would be the optimal ranking here? All the 3 at the beginning, all the 2 after the 3, all the 1 after the 2, and all the 0 after the 1. Because basically you are providing your answer, your ranking list of documents provides first the most positively evaluated documents. Okay? Remember that this number is a number that the judges will give you, that somebody will give you to evaluate the relevance of a document to a given query. Before was either 0 or 1, now it's any number between 0 and 3. Clearly, if I will have 3, the first 2 with evaluated 3, it means that you are providing the most relevant documents before the others. Okay, what is now the discounted gain? The discounted gain is, remember that here we have log of the position. So it's 3, 2 over 1, 3 over 159. Why 159? Because it's log of 3, okay? And thus finally you will sum up, you will get all those results, and the DCG is the cumulative. So 3 plus 2, 3 plus 2 plus 189, and so on and so forth. And we'll give you, this is an evaluation of one ranking, then you will have the evaluation of another ranking, and so you can compare the two vectors. Okay? Okay, clearly you can either normalize those values, but basically you are not, it must be done to contrast queries with a variety number of relevant documents, but does not add anything in terms of concept. So if you understand the DCG is more than sufficient to grasp the idea. Again, first concept, instead of relevant, not relevant, 0, 1, we have a number telling you how much this document is relevant. Okay? And we use this number in the discounted cumulative gain in order to evaluate the quality, the relevance of our ranking list. Okay. Questions? Okay. Let's recap what happened up to now. First, we say how to evaluate the relevance of a result set. Okay, we consider the R-ranked case. In the R-ranked case, we discussed precision, recall, and the combined measure F. And we also discussed why accuracy is not a good idea. Then we say, but look, actually our information retrieval system works on ranked documents. How can I evaluate now two systems? And so we say, we consider precision and recall for each position in our retrieved list. And so we can get a precision recall curve. We interpolate this, or better, precision recall points. If we have precision on the x and recall on the y, we have points, but we want to compare two systems, so we need curves. In order to obtain curves, we make interpolation. So interpolation allows us to compare the two systems, right? Clearly, if one curve is always below another curve, it means that the system is always worse in terms of precision and recall. So no reason to select that system. If there is a crossing point, you can make your choices, whether you want to implement a system that is better in terms of precision, or whether you want to implement a system that is better in terms of recall. Now we say, good, fantastic, curves is good, but it would be better to have a kind of synthetic evaluation. And so we discussed those concepts of average precision recall, mean average precision, okay? Okay. Sorry, and the last point is, okay, and if the evaluation is not binary, is not relevant and not relevant, but actually have a number, a weight, defining to what extent this document is actually relevant, and so we saw the concept of discounted cumulative gain, in which basically we take it also into consideration the weight for each documents in terms of relevance to a given query. Okay. Good. Another mechanism we could exploit in order to evaluate the performance of our system is to try to figure out what is the relationship between the false positive rate. Notice that here is always missing an R, but it's false positive rate, and true positive rate. What are the false positive rate? Are the false positive over the false positive and true negative at a given threshold. Clearly, this number will change. Okay? So, you see here, there is this contribution. Here, there is those two contributions, and so on and so forth. So, I will get a curve like this. Okay? So, what I want to see is at a given threshold in our retrieved document set, what is the false positive rate and the true positive rate? So it's telling me how many relevant documents is giving back to me the system, but also how not relevant documents is giving me back the system. And I want to get an idea of what are the performances with respect to what? With respect to a random system. This line will be clear in a few minutes. Okay, good. So this is the so-called ROC receiver operating characteristic. And basically it tells how much the system is capable of distinguishing between the two classes. And the two classes, in this case, we are back to the case in which we have relevant and not relevant documents. So how much the system can distinguish between those two classes. Okay, let's see those examples. If this is the distribution of true negative, and this is the distribution of true positive, basically those two classes are completely distinguished. And so what I have a ROC equal to 1. Namely, you can exactly distinguish, the system can exactly distinguish between true positive and true negative. Okay? So can distinguish among the two classes that we are interested in. If there is some kind of overlap, the ability of distinguish depends clearly on where do you move your threshold. Okay, and so you have a curve that is something like this. Okay. Now, if the two classes overlaps, so there is no possibility to distinguish between the two classes, because actually the two classes, true positive and true negative, overlaps. So in this particular case, the only option for the system is to guess. You do not have whether it's true positive or whether it's true negative. That's why if we go back to this slide, this curve is random choice, because basically it is the rock curve that you get when you cannot distinguish between the two classes, true positive and true negative. Okay? What is true positive and true negative? True positive and true negative are the set of retrieved documents that are actually relevant or not. Okay? Good. Finally, it can be the case that the system completely mixed up true positive and true negative. What does it mean? That when it observes a true positive, it considers it as a true negative, and vice versa. So, in this case, this is the rock. Okay? So basically, by the rock, you can, and the rock curve, you can evaluate to what extent your system is capable actually to distinguish between the relevant documents and the not relevant ones. And so it's another metric in order to to evaluate the performance of your system. Okay, so again, concept, precision, recall, F. Those are the main concepts. Why accuracy is not important. And then cumulative gain. Okay, when we have an evaluation that is not relevant, but has a value. And the rock curve. Clearly also the precision and recall plot and interpolation plot when we want to compare two ranked results. Questions? Okay, very good, but now the main problem is the following. If we want to apply all those concepts, we need a benchmark, namely a collection of documents in which somebody tells us whether a document is relevant or not for a given query. So the question we want now to address is how can we obtain this set of documents? Okay? Think about it. What kind of problem could we have? Okay, I'll give you a query and a set of documents. I'll give him a query and a set of documents. The problem is that you are independent, and so you can provide completely different results in principle. So we have to reach a kind of consensus, an agreement, okay, on the judgment given by the judges. This is the main issue in technical terms. The other issue we already discussed is that obtaining this kind of benchmark is very expensive. You have to tell to people to spend a lot of time in a quite annoying task, right? Because I give you query, I give you documents, and you have to evaluate whether those documents are relevant or not for a given query. Clearly, if you want a system which is a benchmark, which is interesting, you want a collection that is pretty big, but a pretty big collection means that those guys have to read all the collection to say whether a document is relevant or not. which is actually very annoying. Okay, so again, we have a collection of documents, and what is important is that this collection of documents should not be, in principle, be relevant for the document, for the system we are actually designing, right? We will see that one of the first benchmark available was very limited in scope, and thus it was not significant for a number of purposes in order to evaluate the system. Okay, a collection of information needs, which again is not correct to refer as queries, but anyway, actually we have a pair of documents query, and then human relevance assessment. That can be binary, relevant, not relevant, or more complex, as we saw, a value, a rank, something telling us how much that document is relevant for that given information need, which is represented by a query. We need to pay judges or assess to do this. It's clearly expensive and time-consuming. And what is more important, actually, is that judges must be representative of the user we expect to see in reality. Clearly, if you will take experts about a given topic, most likely those experts will consider relevant documents that are advanced documents, right? Documents that basically provide a very good understanding on the topic they are considering. But maybe they forget that at the beginning of their career, they were a normal user, and so they need more trivial concept to be explained. So basically, you have to reach a trade-off between how much a document is actually interesting, but is interesting for who? For a given class of users. And thus, it's important that judges must be representative of the users that actually will use the system. Okay, one of the first relevance benchmark was this Cranfield. As you see, it's very pioneeristic, but has the real merit of being the first benchmark allowing a quantitative evaluation of information retrieval effectiveness. The main problem is that it's very small. And it's very, I would say, untypical because, come on, not many users are really interested in aerodynamics. Okay, so this is the main problem of this set. More recently has been provided this by the Text Retrieval Conference another set of several different benchmarks. The best known, most likely, is the TREC-ADOC, which has been used to evaluate the system for 8 tracks. And that starts to be very interesting because you have now almost 2 million of documents, so makes sense. Mainly are about newswire articles, but interestingly, you have about 450 information needs. So it starts to be something that makes sense. Clearly, asking to evaluate all those almost 2 million documents for each of the possible query of the information need, it's unpractical, so it's too expensive. And so the judgments are available only among the top key returned for some system, okay? Again, there are other, and okay, now what is interesting is that, as you can expect, the most recent ones are increasingly adding new documents to the collection, and so you have now 25 million of web pages, okay, which is start being a significant number of documents, and you have many others. Okay, clearly the problem is to have a ground truth, namely to have something telling you whether a document is relevant or not, because precision recall requires that you actually know what are the set of relevant documents and not relevant documents for a given query. But the problem is that you cannot expect, as we said before, that all the judges will give you the same judgment about the relevance of a document to a given query. This depends on the background, on a number of cultural factors, right? So the fact is that we need some measure of the consistency of the judgment provided by the judges in order to have the ground truth and to see, okay, if the consistency is above a given threshold, so the value is true or false. Otherwise, discard this value because we cannot reach a consensus. Okay, and this is done by this kappa measure. Okay? So what is kappa measure? Kappa measure, we say, should tell us how much judges agree or disagree about the relevance of a given document with respect to a given information need. It is designed for categorical judgment, and it's defined as follows. Is the fraction of documents, so the proportion of time, by time here we mean proportion of documents, where judges agree, but take also into consideration the fact that you can agree by chance. And this is not unlikely. Why? Why is not unlikely? It's not unlikely because the values are two, 0 and 1, okay? Namely, relevant, not relevant. So even by chance, the fact that two judges will provide you the same relevant judgment is not negligible, can be not negligible. Clearly, if you have a number of values, this is much more difficult. But if you have only two values, 0, 1 is not negligible. Okay. So usually, value of k between 2/3 and 1 are considering it acceptable. When you have smaller values, you need either to do not consider those judgments, or you have to redesign the assessment. Okay, let's make a simple example. Okay, so you have the relevance of judge 1 and judge 2. Okay, so basically they agree in both yes or both no. So both are, they say, are relevant, or both they say are not relevant for a given information need is 300 plus 70 over a total of 400. Okay, and so this is PA, the number of times the judges agree. Notice that agrees does not mean that they agree only on the positive one, but they also agree in the negative one. Okay? Okay, then you have non-relevant, and you have the 80 plus 90. The relevant, 320 and 310. And so what is the probability that they agreed by chance? Is either by chance they will select this, both of them, and so that's why squared, to the power of 2, sorry. Or they both selected this by chance. And so this is to the power of 2. And so you will get 0.6, and the k value by definition is this one, and so you get 0.776, which is okay, according to what we say. 2/3, in the range 2/3, 1 is considered acceptable. Okay, notice that when you consider inter-judge agreement, considering the track data set, the track benchmark, it's interesting that for a number of information needs, actually the disagreement is pretty high. Among 400, remember that they are not considering the whole set of documents, the whole set of about 2 million documents, but only the most relevant ones to given systems. So, as an example, 1/4, in this particular case, there is a disagreement of 1/4. So basically, what we can conclude is that judges disagree a lot, but this does mean that the system, the experimental results to evaluate the performance of the system are meaningless. Absolutely not, because actually you have a large impact in terms of absolute numbers, 1/4, but not in terms of ranking, of relative ranking. Okay? Okay. So, if you want to know whether algorithm A is better than algorithm B, the information retrieval experiment will give a reliable answer to this question, even if there is a lot of disagreement between the judges. Because in terms of relative results, it's still effective. Okay. Now, if this is difficult when you consider standard collection of documents, it becomes almost impossible if you consider the web. Because the size of the collection is huge, okay? So the question is, what can you do in order to evaluate the performance of large search engine? Okay, in principle, the technique we discussed before can be applied, but the cost in order to obtain a reliable benchmark are very high. So what can you do is you can basically consider the precision of the top K, or you can use another technique that is named A/B testing, which is very practical, and it's actually the system that has been employed for the evolution of web engines. What is the idea of A/B testing? Suppose that you want to test a single innovation, so it's a controlled experiment. So you introduce one small change in the ranking algorithm. What you do is the following. In your deployment machine, a limited fraction of the result set is provided by the new algorithm, while the large majority of the result set I mean, the large majority of the queries made by user are handled by the old algorithm. And then you compare the performance of the two systems, okay? And you will basically see whether the system actually are interested or not, whether the users consider effective or not your provided evolution with some kind of automatic measures. So one possible automatic measure, which is not always relevant, is the click-through. So assume that you want to maximize the click-through with your new algorithm. Only a limited fraction of the users are actually redirected to the new algorithm. So they will get the results from the new algorithm. If there is an increase in the number of click-through, the algorithm, after a while, is considered for being actually deployed. Okay, this is a very practical tool that is actually exploited in some system. Okay, just to, I mean, this is a very, I would say, basic discussion about how to provide the results to the user. Clearly, you cannot expect that always the users will click in the link that you provide back in the search results and evaluate the documents and then go back and they click on the second link and evaluate the documents. Usually there is a short summary of the page allowing the user to have a first insight on whether the provided documents is relevant or not for his or her information need, okay? So basically what you do, usually you have very basic metadata, like the title of the document, like the URL, like, I don't know, some other metadata, but is nowadays more common to have a kind of summary. You know, as an example, when you search on Google, you get a very short list of sentences which is a summary. So how to compute this summary in order to allow the user to have a rough idea on whether the provided documents are relevant or not for his or her information need? You have basically two kinds of possible summaries, the static one and the dynamic one. The static one is always the same. So it does not depend on the query provided by the user. The summary for that document is always the same, irrespectively from the query. But you can consider a document that is relevant for a given query, but maybe that the first section is relevant to a query 1, the second section is relevant to a query 2, and so if you provide always the same summary, basically you are not very effective. So this is why you have dynamic summary or query dynamic summaries, okay? In terms of static summaries, usually what is done is that you provide back a subset of the documents. Maybe there are very simple heuristics in which you provide the first few lines of a document. You can have clearly more sophisticated queries extracting by natural language processing techniques some kind of relevant keywords. Do you have in mind, according to what we did, what can you suggest? Do you have any suggestion to distill a set of keywords instead of a summary as the first few lines of a document? You want to provide the keywords of a document. What can we do? we can use TF-IDF, right? That's a good option for us. Why not? TF-IDF is a very good, I mean, the terms higher in terms of TF-IDF are very good. Because they TF-IDF is a kind of fingerprint of a given document with respect to the collection, right? Clearly, you will not provide TF-IDF of all the terms in the documents. It's meaningless, but maybe the terms with the highest TF-IDF. Make sense? That's one possible option, which is actually NLP. Or you can actually have some kind of complex natural language processing that try to synthesize a summary of the documents, but a kind of AI, artificial intelligence technique capable to see a document and to distill a summary in the strict sense, while the alternative of TF-IDF is a list of keywords, the most relevant ones. Here you are actually distilling a summary in the proper sense. Okay. In terms of dynamic summary, basically what you can do is you can have snippets for the basically terms related to the query. Okay, so something like this. You have a dynamic summary in which you outline in the snippets what are the sentences in the documents that are most relevant to the given query. Okay, those are possible examples. Okay, that's it. Are there questions? Okay, see you on Monday.